In this homework problem, we're going to take a look at the XFEM method. Now, I've made a previous video, and it'll be pretty similar to that one. If you've seen it already, then we're going to go over pretty much the same things. The geometry is going to be slightly different, and the partition for the XFEM region will be a little bit different. XFEM stands for Extended Finite Element Method, and it's a relatively recently developed method in the 1999-2000 timeframe. It allows for crack initiation propagation, requires a few input parameters that we need to be careful with, requires a solid element mesh, we can't use a shell element mesh, and it needs a partition in the region to specify the crack initiation. Now this is explained in a little bit of detail in our Abacus manual. So if we come over here and we take a look, and this is section 10.7.1, modeling discontinuities as an enriched feature using the extended finite element method. So it goes into some of these details. And it's fairly interesting. We won't have the time or kind of the background to get into those kind of details, but I encourage you to read through that. Now, the geometry that we're going to use is going to be just a basic plate again, kind of getting back to our plates. And it's going to be 100 millimeters, 200 millimeters wide, 200 millimeters tall. We're going to set a partition in the region. So when I do my points, I'm going to specify a couple additional points. This one's going to be at 100, 75, and then this one over here is going to be at minus 100, 75. This one will be at 100, minus 75. And this one will be at minus 100, minus 75. Now we're not going to connect these across here. That's going to be the basis of our partition. But as we do these points, we're going to go and connect these around in this order. So let's get into our CAE. Okay, you're just going to start with a blank part, and we're going to do a 2D planar deformable shell feature, approximate size 200, and a key in those points. So 100, 100, 100, minus 100, minus 100, minus 100, minus 100, plus 100, and then those 4 points that I talked about that we're going to use for our partition: 100, 75, 100, minus 75, minus 100, 75, and minus 100, minus 75. Alright, so we have those in there, and then we're just going to connect all these up, one to the next one. Now we've done this a little bit already, so I'm going to go through this hopefully a little bit faster. And then we are done with our part. Okay, we can go in and try to partition this right away if we want. We go to Tools, Partition. We're going to partition a face using the shortest path between 2 points. So we'll start with this point over here and this one and create that partition. Now we're going to select this face, and then we're going to go down here and select those 2 points. Okay. So this central region is the region where we'll have our crack growth occurring in. And the reason why I want to do that is I want to isolate it from where my loads are going to be applied, where my boundary conditions are going to be applied. As we know, if we have kind of stiff boundary conditions, we can get some unrealistic stresses near those if we over constrain it. And I don't want my cracks to start right at my boundary conditions. So we'll go done. We'll go into properties. We'll use our basic steel in a Newton millimeter system. addition to the elastic properties, we're going to come down here to damage, retraction, separation laws, and we're going to use maximum principal stress damage. I'm just going to make up a number, 100 megapascals, with a damage evolution displacement at failure of 0.1 millimeters. Okay, and we'll keep the defaults for all of this. All these things are described in the manual, and I'll leave that to you to read through there and glean more information about it. Unlike a lot of our examples, I don't have an analytical solution to show you comparison, but when we do this, I think you'll see some results that seem like they will make sense. Okay, so we're going to create a section. Now this is important. We want to make sure we do a solid section and not a shell. Somehow I got two materials in there. Let's get rid of this. And let me make sure that I have what I need in here. I think it popped up a second material and I filled it out. So let me put in 100 and the 0.1 into material 1. Okay. Now we're going to assign the section. And here we have the properties, material 1, and I think we're okay here. Let's just check that section definition again real quick. Make sure I have a thickness specified. So I'm going to check this box and put a plane stress thickness of 1. Okay. Alright, now I'm going to go to the assembly. I'm going to instance the part. I'm going to create another step, and I'm going to make my time period 100, and I'm going to bump up my incrementation by a couple of orders of magnitude. We'll get into the interaction in a moment. Let's go ahead and specify our loads and boundary conditions through the steps. In the initial step, I'm going to have a boundary condition on displacement. Select the bottom edge and constrain these degrees of freedom. And again, it's going to be a little bit over constrained here, but that's okay for our purposes. And then in step 1, I'm going to create a couple of loads. A pressure load on the top and tension. I'm going to make it minus 90. Now if I went all the way up to minus 100, everything, we get a lot of cracks all over the place depending on what the contours look like. It wouldn't be completely uniaxial tension because we have over-constrained the bottom, but we would have a lot of cracks, and I'm not so sure that's exactly what I want to illustrate right now. So I'm going to make this minus 90, and I'm going to create a second load. We can make it a pressure load, and I'm going to select maybe just this portion up here. And I'm going to have another pressure, and I'm going to make it minus 70. And we'll set these as ramps over the step. Okay. Now we do need to get our crack in here. We're going to go to Tools. Let's see, let's go into the assembly. We'll go Engineering Features, Cracks. We're going to create XFEM, crack 1, and select the domain. Okay, so here it says a single instance or geometric faces. I'm going to go with a geometric face. And so it's going to allow the crack to appear anywhere in this region. And I'll hit Done. And we don't have a crack location already specified. We're going to let it calculate it where it wants to. So we're just going to hit OK. And then the other thing we have to be a little bit careful about is with our field output requests. I'm going to change this to every X units of time, make it every 1 unit of time. I'll put it exact times. And I'm going to add a request every 1 unit of time for, we should have one that says fracture. Here it is. And to see where the crack starts, we need these two, phi and psi. Now we may only need one for a two-dimensional analysis, but basically it's where the crack front is progressing. So we need those in there, and then I'm going to hit OK. And I think we have everything we need. So we're going to go down here and create a job. And we're going to submit it. Now if I've forgotten something, we'll go back and we'll fix it. Oh, I did forget something. I didn't mesh it. Okay, that's important. So we'll go into the mesh. And we'll mesh the part. On the global size, let's say a 4 millimeter global size. So we'll seed the mesh and then we'll mesh the part. Okay, and that looks fine. Okay, so I think I have everything now. Again, if not, we'll fix it. And now I'm going to resubmit this job. And so those two loads, they're going to ramp up over time linearly from the beginning of our time step to the end of the time step. And so we'll probably not see our crack appear until we get a little bit further on in the process. So our crack initiation condition is when the tensile stress, maximum principal stress, gets to be 100 megapascals. Okay, so that's when it will start to initiate that crack. Now due to the locations that we put our load, we would expect to see our crack show up kind of down in this corner. If we're pulling this way and pulling up this way, at some point in time, it's probably going to initiate over here. It may not be at the exact left edge where it initiates because we have kind of the over-constrained condition on the boundary conditions down here. In a physical model, that may or may not be what you want. Okay, so this is running. We can even monitor this if we want. It's pretty common to see these fail if your stresses are too high. The crack gets to be too large. It runs into a boundary or something. It looks like this one made it. Let's see if it initiated a crack. It may or may not have. So we'll go into results. Looks like there's one down there. Now to see it better, I'm going to turn off the mesh. Just show the feature edges. You can show the stresses. And if we animate this, there we go. We see it initiate. And we'll slow that down a little bit. Zoom in on it. And we'll watch where this crack forms. Looks like it forms around here, and it propagates left and right. It's probably hitting this boundary partition line down at the bottom. Okay, so that's pretty interesting. Again, there's nothing that we've put in to tell it where the crack has to form. We've just put some loads and boundary conditions and some parameters that determine the crack initiation conditions. So one more thing that we'll do, just to make sure that this makes sense, let's go back in here to our loads. And on load number 2, we had a minus 70. Let's push it the other way. Let's make it plus. Well, maybe let's make it 90. Okay, so now it's pushing in the other way. Now I would expect the crack to form on the right side of the plate. And so we will resubmit this job. Well, let's make a new job. Okay, and now we've got that submitted. We'll let it run here for a moment. As I said, take a look through the theory manual and read about the extended finite element method. Some of the limitations, some of the capabilities of it are explained in the manual. And I noticed there's a lot of other good examples on YouTube of using XFEM in three-dimensional type elements. My initial goal was to try to have a CAD geometry, bring in an arbitrary CAD geometry, partition it, mesh it, and then use XFEM on it. But I've had trouble finding the right kind of mesh to bring in and apply to this method. Okay, so now this one that said that it's completed. So let's take a look at the results. And it's kind of like what we thought. The crack does form over there. And if we animate this, we'll get to see when it shows up. See the von Mises contours showing you where the high regions are. And there it is on that side now. That's kind of interesting. Let's change this over to maybe maximum in-plane principal stress. So again, down here is where the boundary condition is, but that's not where we allowed the crack to grow. Let's back this up in time just a little bit. Okay, so in this region here is the highest principal stress region in which we are in the crack initiation partition. And so right in the middle of that is where that started. And we can see it growing from there. Now, how realistic is this? In a real material, it would be cracking down here where we've restrained it probably. So you might want to make a change in your component so that you have it larger over here, maybe thicker, and you have thinner over in this section, or maybe narrower so that you can control where that occurs at. You may want to look at crack initiations near stress concentrations. Typically, cracks don't initiate in the interior of a component. Typically, it's a surface phenomenon. But it depends on how it's loaded. Because of the numerical constraint that we applied down here, it kind of has a kind of a peculiar stress field. Where these stresses are kind of higher over in this zone right here. So give that a try. Maybe try a couple different loading cases. Maybe a different geometry even, and write up your report on that. So hopefully this will be pretty simple.